All right, so the first thing is the report for the sulfate lab is going to be due coming up. Right, that's due Thursday for the sulfate lab. Sulfate lab is going to be pretty simple calculation. We want the percent sulfate in the unknown sample. The percent sulfate is going to equal the mass of sulfate over the mass of the unknown times 100%. And so that's basically the calculation there. How do we get these values here? And so the mass of the unknown, you just weighed the sample. You did 3 runs, so each run should have a different mass. Then the mass of sulfate, we just calculate this using stoichiometry. Using stoichiometry to calculate it, what we're going to have is we're going to have the grams of barium sulfate that we captured via precipitation. And so from the grams of barium sulfate, actually I'm not going to write out the conversion back. We convert this to moles of barium sulfate. And then from moles of barium sulfate, we go to moles of sulfate. Because all the sulfate that ends up in barium sulfate came from the original unknown. And so we got 1 mole of sulfate for every 1 mole of barium sulfate. And then from moles of sulfate, we'll go to grams of sulfate, using the molar mass of sulfate. So that's it, just a few steps in the stoichiometry calculation. Are there any questions about this calculation? Should take a minute, or once you calculate the, well, actually more than a minute, because you got to calculate the molar mass of barium sulfate. And then you got to calculate the molar mass of sulfate. And then take a couple of minutes. So this calculation doesn't take long. And so we're going to do one extra calculation with this. We're going to get 3 runs. Run 1, run 2, and run 3. And then what we do is we average those. And so we'll get an average of the 3 runs. Well, the averages, I'm going to talk a little bit about averages. And, how much confidence can we have in the average? Average of 3 runs. Obviously, if we do more runs, the more confidence we can have in that. And so let's talk about the confidence in the average. The confidence in the average, what do I mean by that? Well, I mean this. Let's say you're looking at some two students. Student 1 and student 2. Student 1 and student 2 both get the same average percent sulfate. Let's say that student 1 got 67%, and student 2 got 67% sulfate. Okay, this is the average. And so they both have the same average. Should you have the same confidence in both of them since they got the same average? Would you say? You know, they both got the same average, so those two students are equal. Would you go as far as to say that? Yeah, maybe they had the same unknown. I don't know. I don't know how many unknowns they had, but maybe they did. But let's say when we look at the individual runs, you know, because do you normally just look at the average or do you look at the individual runs? Normally you just look at the average. If you ask your friend, what did you get for your average, right? That's what you do. But when we look at the individual runs, let's take a look at run 1, run 2, and run 3 for student 1. Let's say for student 1 they got 47% on run 1. And then on run 2, they got, I'm going to keep the numbers simple, 87%. And then on run 3, they got 67%. Whereas over here on student 2, on run 1, they got 66%. And then on run 2, they got 68%. And then run 3, they got 67%. You know, should we have equal confidence in both those averages based on looking at the individual runs? No. Because if student 1 did a 4th run, then the average would be dramatically different. Let's say student 1 did a 4th run, a 4th trial, and they got 36%. You know, if they did a 4th trial and they got 36%, then that means their average is going to be pulled way down. And so we're dealing with a couple of things. One is random error, and the other is skill or technique. You know, as far as skill and technique, it looks like student 2 has much better consistency, much better, what we call it, accuracy? We call that precision. We call it precision. The student 2 has much better precision, although they could still be inaccurate. They could still be inaccurate, let's say, because the balance was not calibrated. The balance was reading 5 grams too high. You know, or something. Actually, that wouldn't screw it up. Or something else. You know, they had some kind of systematic error. What we do, why we take 3 runs here, is we try to minimize something called systematic error. We try to minimize something called random error. We try to minimize random error. If we take an infinite number of runs, theoretically, we should be able to completely eliminate random error, because random error, you know, half of them should be too highs, half of them should be too low, so they should cancel out. Unfortunately, we can't take an infinite number of runs. And so the more runs we do, you know, the more confidence we can have that we're averaging out the random error. You know, especially for student 1, we'd like to take a lot more runs. But it turns out that 3 is a very common number of runs. Why? Why 3 runs? Why not 2 runs or 4 runs? You know, have you noticed that? I don't know if you've had enough experimental experience to note that, you know, 3 is typical. And so, is there a reason for and there is a reason for it. There's a reason for it because when we show an average like this, we like to show something that gives us an indication of the spread in the individual runs, and also, you know, how many runs we took. Because there are 2 things that can impact our confidence in this. The 2 things are how broad, you know, what the lowest and what the highest run was, how broad that is. You know, the tighter it is, the more confidence we can have. The wider it is, the less confidence we can have in that average. And the other thing that we like to know about is how many runs we do. The more runs we do, the more confidence we can have in this. And so there are different ways that people show this, this confidence in an average. In science, what we typically do is we show something called the 95% confidence interval or confidence limit. And so when we report an average like this, we'd like to report 67 plus or minus lambda. Oh, this is a different lambda. This is not the wavelength. This is the 95% confidence interval or limit. And what it is just, it's like the statistical number that we put on here saying that, you know, we have like a 95% confidence that the true average is in this range that we're giving here. How do we determine that? We just show you here. We assume we're going to get some kind of distribution of results like this. You know, it'd look like a normal distribution. You know, like half the results are too high, half the results are too low. So we get some kind of distribution like that. And the width of this distribution depends on how many we're taking in the spread. But basically, if we took like an infinite number of measurements, then we aren't. We're going to take a finite number of measurements, and so that's going to impact this. And so we just model this statistically. And I'm not going to get into it, the statistics of it. We're just going to do the calculation for this. So to do the calculation for this, what we have to do is we would have to. Let's go look at here. We'd have to calculate something called the standard deviation. You know, here, and then we're going to use something called the student's t distribution. And then we'll just do the calculation. So the calculation is not that difficult. So let's take a look at doing the calculation here. Here are the equations for this. Let me give you the simple one. Well, first, let's go ahead and calculate some things. So the first thing we'll calculate is the average, which is shown here. That's this x bar n, so, which we did here. We have the averages. So this is our x bar n. Okay, then what we're going to calculate is something that, like the standard deviation for a finite data set, which is variance. This is this S. And so let's go ahead and do this calculation here for the S. And so S is going to equal 1 over n minus 1, the sum of xi minus x bar. And so when we do this, let's go ahead and just plug in the numbers, where n is just the number of measurements. So here we're going to have 3 measurements. So we'll just do 3 minus 1 here. And the sum we'll just do as individual terms. And so here xi would be the first. So we'll do x1, which is 47 minus 67. Yeah, if you square this. So we're going to go here with 47 minus 67 squared. And we're going to take the square root of the squared. Plus the next term. So let's go to x2, which would be 87 minus 67. X2 minus x bar plus the final one, which would be x3, which would be 67 minus 67 squared. So let's go ahead and figure that. This is going to be 1/2 times 47 minus 67 is going to be 20, right? We'll square that. Plus 87 minus 67, that's going to be, this is negative 20. This is going to be positive 20. Square that. And then 67 minus 67 is just 0. Square that. All right, so calculating that, that would be 20 squared. It would be 20 times 20, which would be what? 400? So 1/2, 400 plus 400 plus 0. So just cancel that out. And so this is going to give me 800 divided by 2, which would be 400. Is that correct? All right, then we'll take the square root of this. Square root of 400 would be what? 20? Is that right? 20. Okay. So we get s is equal to 20. And then we have to do this. We have to figure out what our lambda 95 is. And looking at these equations, on Wikipedia, this is too much. Lambda 95 is going to be equal to t s over root of n here. So s, we just calculated that. T, this comes from the table. And n is just the number of measurements. And so I'm going to skip all this other math here. Let me look at it. So what we'll do is we have to go to the table now and take a look. Let's go to a student's T table. So when we look at the student's T table here, we have different values we can select from. Let's see. And so here, what we want is we want this two-tail. These would be the tails here. Two-tail confidence level at 95%. But we can calculate other confidence intervals like 90%, 80%, etc. But the standard is 95% confidence interval. And degrees of freedom would be how many measurements you took. So if we took just one measurement, T would be 12.7 here. 0.7. And so the bigger the T, the wider the interval is. The smaller the T, the narrower the interval is. And the same thing with the standard deviation. The bigger the standard deviation, the wider the interval, the smaller the standard deviation. And so we want a tight, standard deviation. We want a small T value that would give us a high level of confidence. And we want to take a lot of measurements, because the more measurements we take, right, the tighter the interval is. The tighter the interval is, the narrower we can state a range. And so let's take a look at how many measurements maybe we should take in a particular experiment. So I'm going to scroll down just a little bit. And so we're going to focus on this third column here. So if I took one measurement, I have a T value of 12.7. However, if I just take an extra measurement, take a look at what happens to the T value. It drops back down to 4.3. So essentially, it's about 3 times a narrower range. So by taking one measurement, we have a very wide 95%. But if we take 2 measurements, then that narrows down by about a third. If we take 3 measurements, what happens? Well, we go from 4.3 to 3.1. It wasn't as dramatic as taking 2 measurements. Taking 2 measurements, we can have much greater confidence in that average. Taking 3 measurements, well, it's better, because now it's at 3.18. And so that's definitely better, but not the huge jump in confidence that we have here. But if we go from 3.1, let's take 4 measurements here. Well, 4 measurements is better yet, right? 5 measurements, better yet. 6 measurements. But take a look at the difference. If you take a look at the difference between 5 and 6 measurements, is it a very large difference in the T value? No. And so as we go down, we can see, like, the difference between taking 29 and 30 measurements here is 2.045 versus 2.042. And so not much of a difference there. Obviously, the more measurements you take, like 30 measurements versus 3 measurements, 30 measurements is going to be a lot better. And so normally 3 measurements is taken, although more measurements is always better. But 3 measurements is taken because that's pretty much what you don't want to go below. You don't want to go below 3, because then it widens out quite a bit. And then it depends on how easy it is to take additional measurements. If it's very easy, then you can take a lot. If it's very difficult, like this sulfate, then is it really worth a little bit of extra confidence, for all the extra work in taking a 4th measurement? And so 3 is a pretty good compromise in terms of minimizing our random error versus minimizing time in lab. And so, and so what we'll do is we'll just go ahead and plug in the numbers in here. And so we could just do T. We took 3 measurements, so what is T for 3 measurements? Do you see it? What is it? 3.1824 times S, which we just calculated, 20, divided by the square root of 3. And that gives us what?
$36.74.
36.74. Okay. 36.74. And so what we're going to get here is this. The student 1 is going to have 67 plus or minus 37% sulfate. And so that means that they have, based on the statistics of this or whatever, they have a 95% confidence in finding the average in this range. The range would be from 30 to 104%, although 104 is not possible. So between 30 and 100%. So, okay. What about student 2? Can you have a high degree of confidence in this average here? Would you say? No. How about student 2? Can you redo the calculation for student 2? And see what it comes out to? They had the same average. They had the same number of trials. So they had the same average, they had the same number of trials, so T is going to be the same, N is going to be the same. What's going to be different? What's going to be different is what they call the standard deviation. If we had an infinite data set, 95% confidence would come in at 1.95 times. And so this number eventually, once we get to n equals infinity, is just going to drop down to, well, actually, well, anyway, let's go ahead and calculate that and then tell me what you get.